Well, here we are. We made it to the last regular class. So if I read the final exam thing right, it's what, Thursday? Next week at 10 a.m. So whatever, I think I put it on the Canvas page. So again, if you're in the section that's, you know, the big section that are come to class, if you're in the other sections that are offline, I'll be sending you the exam. If you're in the class and you have some valid reason why you can't be here that day, send me a reminder message. So, although I'm way behind on my Canvas messages, we'll try and get caught up here. All right, find a little bit of chalk. So what we're looking at was quaternions. We wanted to give you enough, background. So if you run into them, and boy, you run into them all the time now. So what I showed was I guess it was out of geometry messages from ROS 2. And one of the geometry messages, so it's standard messages that can be used to pass data between processes. And one of them is a pose message. And a pose is a position orientation. So basically you want to know all the information to know the relationship of coordinate system B back to A. And the way that they showed it in that geometry message was there were two parameters in the message. One was a point, and we looked at that message. It had doubles or floats, X, Y, Z, so there were three numbers, which kind of made sense. And again, those numbers would have to have units of length. And then for the orientation part of the relationship of B to A, they just said, hey, here's a quaternion, 4 numbers. Now they call them X, Y, Z, and W. We call the X, Y, Z ABC and the W D, but that's the only difference. So if we showed last time that if we had two quaternions, so if I had D1 times the quaternion 1, and a lot of times we don't even write the quaternion 1, because that's the scalar part, plus A1 times the I quaternion plus B1J plus C1K. And then we had a second quaternion, D2, A2, B2. And we talked about addition and subtraction. Those are pretty easy. And multiplication, though, the rule was really important. And it was all due to Sir William Hamilton. And we saw the story about he was walking to some meeting across the Brom Bridge. And the definition that he wanted for quaternion multiplication just came to him because he was able to see why that definition was going to allow him to do good stuff. And here's what he came out with. He said, if you take two quaternions and multiply them, you're going to get a quaternion. The scalar part was going to be D1, D2 minus A1, A2 minus B1, B2 minus C1, C2. So I could take all that and say it's times the quaternion 1. Well, what the heck, I'll go ahead and do it. A lot of times you just don't write that one for the scalar part. And then the easiest way to remember the rules was to say, it's the scalar part of the first one times the vector part of the second one. And then we had the scalar part of the second one times the vector part of the first one. And then the last part was easiest to remember from this determinant. Put these quaternions I, J, K, then put the vector part of the first one, A1, B1, C1, and then the vector part of the second one. And again, if you work all that out, you're going to get something times quaternion 1 plus a bunch of stuff times I, a bunch times J, C, and so you get a quaternion. So it doesn't seem at first glance that this is really going to do much for us. And his kids said, can you multiply vectors? So what they were calling the vector part would have been if D1, D2 were 0. And this kind of reduces down to, it's like if they were vectors, it's negative, the dot product is the scalar part, and the vector part just is the cross product. That's kind of wild. So it looks like quaternions can combine a lot of stuff. If you did quaternions where these B's and C's were always 0 all the time, you pretty much got complex numbers. Because I times I is -1. And so you kind of have all these domains can be modeled up with these quaternions. So that's what we did last time. About division. What we saw was that the norm of we started off with the conjugate of a quaternion. So if I said the conjugate of Q1, it's to negate the vector part. So it'll be minus A1I minus B1J minus C1K. And then we found that if we took that conjugate and it turned out on this one, because when the order matters, but the order, you can switch the order if this determinant goes to 0. So if these directions are parallel to each other. So if I take q times its conjugate, that does happen. So I can, that is going to hold that special case. And it turned out that when we did all that multiplication and looked at what happened, this canceled that, this went to 0. Because we had a negative on these guys, we wound up with, what, d1 squared plus a1 squared plus b1 squared plus c1 squared. And we called that the norm of this, q1. I'm going to say q1, q1. So the norm was just that product. And again, it's a scalar value, so like we did some examples with scalar stuff where we called them like lambdas and mu's and saw how, for example, lambda q equals q lambda, all that kind of stuff, because it's just a scalar. So if it's just a scalar, we could go ahead and divide this. So I've got this. I'm going to divide by that value, so I get 1 over here. I'm going to put the norm, it's just some scalar. I'm just going to divide it under that one. And when we looked at it, we said, well, that's definitely going to be a quaternion. And boy, it's a special quaternion. When I multiply that by q, I'm getting 1. So we're going to call that the inverse. So whenever we didn't do pure division, of quaternions, but we used that inverse in equations to, be able to solve stuff. Okay, so with all that, what we're supposed to do today is to say, how do we apply these things? And what we're going to do is, I'm going to present it the way it is in the book, and then at the end, I'm going to make a slight change that I think is nicer, but here we go. So let me put this picture up. I think that'll be easiest instead of me drawing this. We're going to do this problem where we're going to say, imagine there's some point in a body, and we are going to rotate that about an axis, in this case, S. I don't know if I put S and then I've got, the R. That's okay. Oh, no, I got it. Okay. So this S, if I can find my pen here, is, again, I'm thinking of it in the vector world now. It's some Sx times I vector, Sy, Sz. And our criteria is that this is going to be a unit vector. So I've got a point that is designated, its coordinates are given by r. And I want to go ahead and take that point and I want to rotate it about an axis through the origin. It's going to wind up over here at r prime. Now this is the angle this is what I did in the book, is I said the angle we're going to move is 2 theta. And what I'm going to do at the end is I'm going to redo the problem statement and say, no, it's theta. And then in our result, in this result where I see theta, I got to put theta over 2. So we'll see that at the end. But this is the problem that we want to look at, is to say I've got this point in a body R, and it's been rotated about an axis through the origin by an angle 2 theta, and it's going to wind up over at r prime. And so can I calculate r prime? So we know how to do that in a rotation matrix way. So imagine we had a coordinate system B is, initially aligned with A. And I know, what should we call that? 0.1. I know 0.1 in the A. And I'd like to find out, where the 0.1 winds up after it's been rotated. So what I'm going to do with our rotation matrix is I'm going to pretend that the point didn't move, but I had coordinate system B rotated -2 theta, right, about S. Okay. So coordinate system B is going to be rotated -2 theta about, the unit S. S is given. And if I can find, that coordinate of that point in the B, that's going to be the answer to this problem. So again, in this problem, I'm thinking of it as the coordinate system hasn't moved and the point is moving. I can solve it with what we did by pretending the point didn't move. I had a coordinate system that went the other way, and I'll get that point in that other coordinate system. So are you okay that they're equivalent problems? Yeah. And we know how to do this. I mean, shoot. And we're going to do it a little bit later on and see what the answer came out to be. And we're going to compare it to what we're going to do next, where we're going to solve this problem doing quaternions. But this is how we would do it, based on what we know so far. So part of this is, well, then why are we doing this, right? We've already got all the tools that we need to solve these problems, But let's see how we're going to do this with quaternions. And when I was putting the book together, I couldn't think of a great way to sort of show this. So I call this the sledgehammer approach. We're going to make this magic hypothesis and say, hey, this might get us the answer, and we're going to work it all out with quaternions. And then we're going to work it out this way, because we trust this way, and we're going to see this the same answer. So it doesn't give any indication of how did, I don't know, he's crossing the bridge and he knew this was going to happen? I don't know. So again, I kind of did this sledgehammer in the book. Okay, so we know how to do it over there. So it's funny, I really don't want to erase that. And I do have it all in the PowerPoint, but then sometimes I hate just, PowerPointing it. But here's what we're going to do. We're going to look at this problem and say, yep, I got this unit vector S is given. So I know, Sx, Sy, Sz, and they all have to, sum of the squares all have to add up to 1. I'm going by this angle 2 theta. So here's our hypothesis. We're going to go ahead and generate 2 quaternions. So the first quaternion is going to contain information about the point R. So again, I should have said given, right? Given and find. So we're given Sx, Sy, and Sz, and it has to be a unit vector. And again, I've underlined those because sometimes like these, is it a vector? Is it a quaternion? No, those are vectors. That's what I'm used to. And I'm also given this vector R, Rxi plus Ryj plus Rzk. And again, that's not a unit vector. That's the coordinates of the point that's moving. And what I want to find is, I just called it R prime. So I could say I want to find, R prime has some R prime xi plus R prime yj. And I should have probably written on the board because that looks so bad. But again, we're given the unit vector, we're given the coordinates of that point. I want to find out where did that point go to. I know how to do it with rotation matrices. I would put a coordinate system B, rotate it -2 theta, find out what it is in the B, and I'm done. But here's what we're going to do. We're going to take the given information and we're going to form up 2 quaternions. So these are quaternions now. So this quaternion I'm going to call R. So again, these are not underlined. These are quaternions. And I'm just going to form it up based on the given stuff. These were the coordinates. So again, they'd have units of length and stuff, but that's okay. So those were those given coordinates of the point before it rotated. And then here's kind of the magic one. I'm going to form another quaternion. Oh, notice how this one has no scalar part. It just has a vector part. I'm going to form another quaternion. And the scalar part is going to be cosine of half the angle of rotation. And the vector part is going to be sine of half the angle of rotation times, again, Sx, Sy, Sz. Those were the components of the axis vector, where, again, the Sx squared plus Sy squared plus Sz squared is 1. So we're going to form up those 2 quaternions. So making those quaternions is really easy, right? I mean, shoot, based on what we're given. And then here's our magic hypothesis. We're going to do this quaternion Q times R, and the result of that times Q inverse. And we are magically going to get the coordinates of that point after it's been rotated. So I'm not doing any proof. It's like somehow this magically popped in our head, and then we're going to compare it to how we know how to do it with rotation matrices and say, oh yeah, it came out the same, so I don't know how you thought of that, and so I feel a little guilty about doing it that way in the book, but I just didn't know what else to do at this point. And I was pretty tired. It was chapter 12. Okay, so that's the plan. So the first part is, based on what we're given, can you form up those 2 quaternions? Yeah, no big deal. Can I do that math? Yeah. Well, we're going to go ahead and multiply this all out. Oh, what I'm going to do at the end is I'm going to change the problem statement where I'm going to say, I'm just rotated by theta, so then this becomes that. And I like that better. you know, because I'm not going to remember that, oh, that, you know, I'm going to say the point was rotated 60 degrees, and I got to remember, oh, that's 2 thetas. And so if I were to redone the book, I would have just said that was theta, and I would have put this theta over 2. I just think that's easier to remember, but it's equivalent. So there's no big change at the end, but that, when I do problems, that's the way I do them. So really easy to make those quaternions, and if this is true, you know, the quaternion multiplication is not too bad, you know, it's not terrible. Okay, well, hey, what about this quaternion Q? Let's go ahead and calculate its norm. So we're going to take the given stuff. I shouldn't have written that so big because I kind of don't want to erase it. We're going to need it later because we're going to do that problem and show that it's the same. So we formed this quaternion Q, so it was cosine, this was half the angle of rotation, sine of half the angle of rotation, and then it had well, Sxi plus Syj. So what would the norm of that be? So the norm was, right, d squared plus a squared plus b squared plus c squared. So the norm becomes, you know, cosine squared. I can pull this out, and I'm going to wind up, again, when it's a squared plus b squared plus c squared, I'm going to get that. Oh, hey, that was a unit vector. That went to 1, sine squared, cosine squared. So this quaternion that we formed up out of the given information is a unit quaternion. And that's important to us. It's always going to be a unit quaternion, no matter what as long as the S vector was unit vector. It doesn't matter what the angular rotation is. This Q that we formed is a unit quaternion. So that's just good to know. We'll get rid of that. So if that's a unit quaternion, let's look at our hypothesized, I'm going to get rid of this junk here. I got a little bit of board space now. So we're going to say that, Q, R, Q inverse, where we know we formed up Q and R based on the given stuff. Again, when we multiply this all out, though, we are going to get a quaternion, right? Because it's quaternion, multiply, you get a quaternion. I sure hope that this quaternion that we get has no scalar part, and I'm hoping that its vector part is going to be the coordinates of that point after it was rotated by 2 theta. So let's start off, let's look at the norm of whatever this result is. Oh, we saw that, you know, one of the things we talked about in the other class was if so Q is equal to Q1, Q2, Q3, the norm of Q is the product of the norms. So that's why we did it, was for this today. So it's going to be the product of the norms. Hey, this is a unit quaternion, so this norm went to 1. Oh, Q inverse is sure easy to calculate, right? It's the conjugate divided by the norm. The conjugate is to put a negative sign here. So, right, Q inverse, so it is kind of nice. Getting the inverse is like no work at all. Right, it's going to be cosine theta minus sine theta Sxi plus Syj. So its norm is also 1. So one thing that I notice is whatever this crazy thing is, I am going to get a quaternion whose norm is the same as the norm of quaternion R. And you say, well, why that's important to us? Because what is that norm of quaternion R? So if we look at it, you know, I go back to this. Here's what R was, right? It was the coordinates of. So if I take the norm of that, right, I'm going to get, well, there's no scalar part, so I take that squared plus that squared plus that squared. And what does that physically represent? That's the square of how far away the point is from the origin, right? If I take the square root of that, I'd have the distance. So it's kind of nice that when I calculated this, I got the same norm. Because if I rotate about an axis to the origin, the point's not going to get any closer to the origin or further away. So right off the bat, that's a good sign of what's going to happen. We have to do the multiplication because I sure would hope that this has no scalar part. And then I hope the vector part of it does give us the coordinates of the point after it moved to the position of R prime. But that was a good sign anyway, that that happened. So we need to go ahead and take our Q and our R defined based on what we're given. We're just going to brute force this and see what we get. And then we're going to do this matrix, rotation matrix one and see what we get. Boy, they came out the same. So my goodness, then this is kind of useful to us then. Okay, so here we go. This is again what was given. We're going to go ahead and say we're given, there's some point R, we know its coordinates, and it's rotated about the unit vector S by an angle of 2 theta. And what we're going to do is make this hypothesis. We're going to say that R is going to move to R prime, where R prime, I sure hope, is going to have no scalar part, and the vector part is going to be the coordinates of that point after it's been rotated 2 theta about that axis through the origin. So we're going to define Q. And again, this is half the angle of rotation. And R is a quaternion we're going to define based on the coordinates of that point. And you said, no, yeah, Q was a unit quaternion, so that was cool. So that's our problem statement, and we're just going to brute force this. Like I said, it's like taking a sledgehammer and just, we need to do this multiplication. Oh, here's our definition of multiplication, which is already on the board. So we're going to just apply that. First thing we're going to do is multiply those two together. And I think I'm going to call that, Q times R, I'm going to call it T. And again, we're applying this rule here, so it's kind of like, we can go through and, follow up. We're going to do all this, but at the end, you say, okay, I believe you, they came out the same. It looks like it's working. But here we go. So Q times R says, according to this definition of multiplication, is, let's see, I get D1, D2. Okay, here's D1. D2 is 0, right? The R quaternion had no scalar part, so that term is nothing. And then we get, negative A1, A2. There's A1, there's A2, there's negative A1, A2. Negative B1, B2, sine theta SY. Yep. Okay, so there's our scalar part, right? That's all times the quaternion 1. Okay, then we come over here and we had the scalar part of the first times the vector part of the second. And then this, this part, because that went to 0, the second one, R, doesn't have okay. So then we wind up with ijk quaternions times the vector part of the first one, which is Q. So I pulled the sine theta out front, and the vector part of the other one. So there's no magic there. It's just like, it's kind of tedious, really. Although, if I could have gotten Maple to fire up, Maple doesn't mind expanding that all symbolically. So assuming I did this correct, this is what that first product, Q times R, was. Let's see. I grouped everything together. Here's all the stuff that's times 1. I took everything times I, everything times the J quaternion, and just cleaned it up. And then I said, this is starting to get out of hand because I have to next do T times Q inverse. So I said, for now, I'm going to call that D and call that A and call that B and call that C. So I can, and then we'll substitute this in later. So now I'm going to do the T, which was that, times Q inverse. And again, the inverse of Q is the conjugate over the norm. The norm is 1. So the inverse is the conjugate. So again, from a computer point of view, boy, that's quick to calculate. Not many additions and multiplications required to get that. So here's T, and the conjugate of Q was, here's the cosine of half the angular rotation, and we put a negative on the vector part, and just started, this times D1 times D2 minus A1 times the A2. There's a minus sign, so I get a plus, so this takes care of those terms. The scalar part of the first times the vector part of the second. Scalar part of the second times the vector part of the first. And so again, no magic or anything. So we're brute forcing this. I'm going to hit down and, we're going to go ahead and look at the scalar part to begin with. All right, that's all the part times the quaternion 1. So let's look at that. So I wrote that over here. And it says substituting the expressions from equation set 1250. So if I go back, where was 1250? Remember when it was getting complicated, so he gave them names? I'm going to substitute this junk now back into that scalar part of r prime. And when you did, although I'm not really showing all the steps, I got this result. And if we look at this, look at, here's a negative sine theta times an sx rx. Here's a plus sine theta times an sx rx cosine. So those are going to cancel. Whoop. And if I go through, they all cancel. So right off the bat, all we did is brute force this, but we went ahead and did that multiplication. And based on our definition of Q and our definition of R, that R prime quaternion has no scalar part. So that's a really good sign. I mean, if that didn't happen, I'd say we're not going to get the coordinates, because I get this quaternion, I don't know what to do with it. But at the moment, we see that crazy product, QRQ inverse, where it was real easy to build Q and R based on the given stuff, we do get a quaternion that has no scalar part, and the norm of that quaternion, the R prime, is the same as the norm of R, which geometrically sounds good to us also. So what we have to do is finish the sledgehammer problem. We already told that story about the norm. The vector part, I'm not going to go through all the steps, but I kind of did not too bad, only like skipped one equation here. And I'm going to call this the final result. So, looks kind of ugly, but if I calculate R prime, I get a quaternion that had no scalar part, and the norm is the same as the norm of the original one, and I got all this crazy junk here. So what we're going to do is solve the problem the way that we talked about with rotation matrices, and you're going to have the exact same crazy junk. So I said, wow, I guess it worked. So again, to solve it the other way, we're going to say, okay, I know the coordinates of this point, so we're going to call that rxi plus ryj plus rzk, so I know these numbers. We also know we also know the s vector. That was sxi plus syj plus szk. And based on the given information, we're going to say coordinate system B was initially aligned with A. It was rotated -2 theta about this unit vector. So we know how to get the rotation matrix. What would that be? B to A? So, shoot. Let's go ahead and I bet you it's going to be in the PowerPoint. Oh, yeah. So what we did in the previous part of the book is we said if B was aligned with A, and it was rotated, theta about mx, my, and z. That top, matrix was where the V was the verse sign. So what I plugged into that top expression for the theta term, I plugged in -2 theta. And for mx, my, and z, I put sx, xy, sc. And if you do all that, you get, I guess I called it D was aligned with C, but you get, that matrix. So what we got on the board, though, is, based on that stuff in our problem statement, we know how to get that. But the point is known in the A, I need to get it in the B. So I need to transpose that. Right? I need A to B because I'm trying to transfer from the A to B. So we're going to take that result that's on the bottom of that PowerPoint slide and just transpose it and brute force the heck out of this. So here it's talking about how we had to, get the inverse or the transpose in this case. And so I went ahead and, again, transposed that and did this equation. So I had this R on the board here. I'm calling that now, B was aligned with A. All right, because the origin didn't move, so I don't have any extra term or anything. So basically, we're going to go ahead and do this calculation. It's just in my PowerPoint. Instead of A and B, I called them C and D. And this is what I got. Okay. Did a bunch of math on it. So that was, and I don't feel like doing the math today, right? But I got that result, did some math. That's probably 1265. Did some math, did some math. And then if I compare this to what we got for R prime, that is that, and this, right, is the J, and Again, it would have been nicer to kind of go through some proof of why QR Q inverse was doing this, but I just sledgehammered it and say, I knew how to do it with rotation matrices. I got the thing that's on the top of this slide. And when I did that quaternion multiplication, I got the stuff on the bottom. Okay, I'll believe it. We'll go for it. Okay, let's take a look at, on the note thing. There was two things. One of them was a spreadsheet, and one of them was a spreadsheet. The other one was a Maple file that I couldn't get Maple to run today. So let's see where I put the spreadsheet. Because last time we looked at the spreadsheet, there was one thing on top that seemed like it was kind of useful. And again, you're welcome to use this on anything you want. The top element just said, again, the yellow indicates where I would type stuff in. So it was, the top one was given two quaternions, Q1, Q2, just multiply them out, and there's the answer. And this is the one that we just did. Suppose I was given the angle of rotation, so that's my 2 theta. And I did not put it as a unit vector, but look at what I did in my calculations. I immediately calculated the unit vector. This is the axis, and this is some point R. And I've got some intermediate calculations here. I showed this is what I got for Q, right? So it's cosine of, and again, I'm going to call this theta, and I'm going to say it was the cosine of theta over 2 plus sine theta over 2 times the vector, unit vector axis. Oh, Q inverse is the conjugate. So yeah, these last 3 numbers are the negatives. Here's the Q times R, that was the T term. So I did it just step by step. And again, if you click on these cells, I mean, there's no magic here. It's just oh, it won't let me edit, that's okay. And then finally, here's Q, R, Q inverse. And so that represents the coordinates of the points after the rotation. I went ahead and I said, based on point R, I did the square root. So I said, basically that's telling me how far away was the point R from the origin. And over here, I did the square root of the sum of the squares, and I got this, it was kind of a check. Right? The point better not be any closer to the origin. So as far as the calculator, it's kind of handy. And then we got one other thing we're going to do, and this has to do with our orientation stuff. Any unit quaternion represents an orientation relationship between 2 coordinate systems. So if I was given a unit quaternion, and again, if you don't give me a unit 1, I unitized it in the calculation, I would like to know what's theta and S, so I can take that unit quaternion and in my head have some geometric understanding. So here's the answer, and then here's the S. And it looks like I put in the numbers, let's see, I took these numbers for Q and put them here, and I better get like 39, and right, I better get, as a check. Look like there was a little bit of round off here. So that's the next problem that we want to do, and then we're going to look at 3 problems in the book. Okay, so we brute forced it, that problem of moving that point by using rotation matrices, by having coordinate system B rotate the other way. And we saw that it was equal, to the result we had. So now I'm going to say, imagine I'm given a unit quaternion, and I'll just call it, I'll put a 1, I'm used to that. So I've got D1 plus A1I plus B1J plus C1K. And it's subject to this. It's, a unit quaternion, so the norm equals 1. I would like to be able to look at that quaternion and say, what the heck are, it represents that this body has been rotated by some angle theta about some axis S. I'd like to know what that was. Well, I know right off the bat that this D1 has to be the cosine of half the angle of rotation, and I know that A1 is sine of half the angle of rotation times Sx, and I know that B1 is the sine of half the angle of rotation times Sy, and I know that C1 is the sine of theta over 2 Sc. So let's go ahead and put numbers, and shoot, the numbers I got on the screen there are as good as any. 0.943. So if I use this one as an example, .0728. And let's see, B2914. And what's that one? Negative 1457. So if I had those numbers and I know that this is the interpretation of those terms, I'm going to start off with the top one. So I'm going to say that cosine of half the angle of rotation is 943. Is that right? Yeah, 94264. So then we're going to go to our calculator and say, let's inverse cosine. And again, you ought to be a little bit nervous because if all we know is the cosine, right, there's two angles, but okay. Let's see what the calculator tells us. So I'm going to take 0.94264 and I'm going to do inverse cosine. So it's saying that half the angle of rotation, the calculator told me, is 19.5. So right off the bat, I'm saying, well, theta, 19.5. So it's either 39 degrees or negative 39 degrees. Because all I knew was the cosine. And again, you got to be careful to remember that that thing that came out of the calculator was half the angle of rotation. Okay. So I'm a little nervous now because we're going to go ahead and take, if it was 39 degrees, we're going to go ahead and solve for Sx. Oh yeah, so if it was 39 degrees, I'm going to put the sine of 19.5, and I'm going to divide the A1 by that value. Oh, okay. So we go to the calculator. So we're going to do the sine of 19.5. And what have I got to do with that? I've got to divide that into A1. A1 is 0.0728. So I'm going to divide it, and then I'm going to 1 over x it. So it looks like we're getting, for this case, Sx is what, 0.218. And I'm kind of looking at the PowerPoint to see if we're the, oh yeah, you see that number right there. It's matching up. And again, I can do the same thing. I can say for, if theta is equal to 39 degrees, I can take that sine, divide B1, which is given, and I get S1. So yeah. And then I'm going to come in and I'm going to take the negative 39. And I'm going to say, oh yeah, there's another possible answer. Okay, the sine of negative, 19.5, because I got to divide by 2, is equal to the negative of the sine of positive 19.5. So this is going to have the same magnitude, but a negative sign. So when we solve for Sx, we're going to get the same number, but with a minus sign. So over here, Sx would be minus 0.2181. And when I got Sy, this Sy is going to be the negative of that one. And when I get Sz over here, this one. So what this is telling us is I take this unit quaternion, and it says, yeah, I can think of it as the body was rotated 39 degrees about this vector, or negative 39 about a vector pointed the other way. It's physically the same thing. So I'm like, yeah. So these four numbers, though, gave me this interpretation. So again, why are quaternions, because the other question was, these are four numbers, why didn't we just say, define the relationship as, the body's been rotated, theta about some S vector? Because the orientation you get has two possibilities. It could have been negative theta by the negative S vector. I don't even want to be able to have those two. So almost think of it as a forward and reverse problem. The forward was given the, B's aligned with A, and it was rotated theta about, and you get the rotation matrix, fine. But given the rotation matrix, I want to go back and get S and theta. There's two answers. So I guess what I'm saying is that if you wanted to represent the orientation by the four numbers of theta, and then boom, 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 that orientation you had could have been represented another way. So like every orientation has two names. When I represent that orientation relationship with quaternions, they all have one name, one quaternion. Because when we interpreted that quaternion, we got both of those interpretations out of it. But as far as if you want this orientation, these are the 4 numbers that represent that orientation. So you don't have the double up trouble that you have with just thinking of, the physical rotations. And you don't have that singularity thing. If you did Euler angles, like rotate about X, then Y, then Z, and then you got into that one weird case that might happen. So that's why quaternions are super popular, is every possible orientation has 4 numbers. So the way that when it's used in Ross, and you'd say, I'm trying to represent the orientation of, it might be a drone or something like that. So we'll go ahead and have a world system where usually what we wind up using is called easting-northing coordinate system. It's something called UTM coordinates. You are going to have a reference for your origin of the world. But we put the X of, I'll call this the A coordinate, is along the eastern, pointing east, and the Y is pointed north, and the Z is up. And then if you want to describe of course, the position of the drone, there's a drone coordinate system. So we'll call that the B. And again, the position is defined by, what's the coordinates of that point. So nothing we're going to do different there. But in that message that described pose, they did the orientation based on the quaternion. So they would say, B was aligned by A, and it's been rotated, some 2 theta about some S vector. So the orientation is going to be represented by a quaternion of those 4 numbers. Again, if you know I like to think, in the S vector and the theta. So when I go to build the quaternion, I'm doing this. All right? This is the quaternion. Of course, they call it X, Y, Z, and W, but it's pretty easy given the angle of rotation and the axis. It's pretty easy to build that quaternion. And then that's what's put in the message to say this is the pose, position, and orientation of that body in space. Okay. So it's used a lot. And it's because this orientation, there's only one quaternion. So there can't be any ambiguity or mix-up or anything else. Okay, so we got to do 8 minutes. We got to do 3 problems in class. Again, this spreadsheet does do that problem. Given a quaternion, I make sure I unitize it, and I do calculate. These are some intermediate calculations. I should have put these in a different color, I guess. The actual outputs are, theta and the S vector. So, and again, you can use this as your calculator or whatever you want to do with it, it's fine. The Maple file has some functions to do quaternion multiplication and all, and I wanted to run it today, but it was not cooperating. Okay, so what are our problems? So in the book, there's 3 of them. So here's a body, and let's see, the body is shown in the picture, and it's rotated about an axis M. So it's not unitized yet. Okay, and here it is. It's in the XY plane. And it was rotated by an angle of 60 degrees. So it wound up in position 2. Then, let's see, it's rotated about this new axis, which is not unitized yet, by 115 degrees. There's some point in the body, 5, 2, 3, and I want to know where that point wind up after the 2 rotations. Now, what's kind of interesting here is this, and it's said in the sentence here, is both M1 and M2 are measured with respect to the XYZ. So in this problem statement, there's one coordinate system shown, and the M vectors are both in that, and it's going to be a really easy calculation. So first thing we're going to do is I'm just going to call that point, R, so we know the coordinates of the point in the body. So if I want to find out where the point wound up after the first rotation, I'm just going to go ahead and make a Q, which is cosine of half the angle of rotation. The angle is 60. So it's going to be a cosine 30 plus sine 30 times, I have to unitize the M1. I'm just going to write it like that. Okay, so if I do this operation, I'm going to call it in position 2. I'll say in position 1, I knew it. So it's going to be Q, R, Q inverse. So that's where that point wound up in the second problem. Okay, then we're going to say, now I see this thing and it's in position 2 and it's been rotated 115 degrees about that M2 axis. So we're going to go ahead and do the problem again. I'm going to make a new quaternion that's the cosine of, 115 over 2 plus the sine of 115 over 2 times, I call it M2, but I had to unitize it. And I'm going to take the point from where it was in position 2, and I'm going to say at position 3, it's going to be Q2, R2, Q2 inverse. And we're done. Let's go ahead and substitute this in here, though. So I could say R3 is equal to Q2, Q1, R1, Q1 inverse, Q2 inverse. And when we multiply that all out, the order doesn't matter. So imagine I went ahead and sort of grouped it like that. And I look at, Q2 times Q1, and I know when I multiply them, I'm going to get a quaternion. Those Q2, Q1 are both unit quaternions, so their norms are 1. The norm of this product is going to be 1. I'm going to call it Q3. Whatever that multiplied out, it's going to be a unit quaternion. And look at what it's doing. It's taking it directly from position 1 to position 3. So that quaternion is giving me all in one step. And then you look over here, and remember we did a thing that said that if Q3 was the product of two quaternions, the inverse of Q3 is equal to the products of the inverses in the opposite order. That's why we did it on Monday. Because this is Q3 inverse, yeah. So Q3 is the magic quaternion that would have done that motion in one step. So that was kind of cool. But for the problem, what was given, it said, just multiply this out, and that's going to tell you where that point went to. But when you look at problem 2, where's problem 2? For the previous problem, it said, what is the axis and an angle that would take us from position 3 directly back to position 1? We just solved it. Right? Q3 is a quaternion that went from 1 to 3, so I'm going to interpret Q3. What's its theta and what's its axis? To get back home, I'll go negative theta about that axis. So we got problem 2 is done. So it's not, other than, quaternion multiplication being kind of a pain and a lot of steps, it's pretty easy to wiggle around with these. So that's all problem 2 was. What's problem 3? I forgot. What was problem 3? I got the book here. I'm glad I brought it because I don't see it in here. Because there is something about problem 3 that I wanted to mention. Chapter 12, quaternions. Problem, okay, we got a couple of minutes. We're going to just make it. It's kind of weird. We get all the way to how many weeks and things and going through, and here I am trying in the last 2 minutes to get to the last problem. It's like everything kind of worked out. Okay, what was problem 3? Example problem 1 to problem 3. So here's what I want to say about problem 3 is read it after the test, right? It's asking something that is not worth asking. I'm going to kind of leave it at that. I'm not going to ask something like that on the test. It's trying to do this other interpretation that is just too much. It's just kind of crazy. What we had just done was kind of the important part, was to show that after those 2 rotations, we can interpret the result to what it would have taken to move from position 1 to 3 in one step. We can interpret that. And it's pretty easy to work with. You got the spreadsheet thing there. I moved that due date for the reverse analysis because I was doing okay, and then between the 2 classes I still have like 30 things in my message thing that I haven't gotten through. So I felt kind of guilty if people had questions on the homework and I wasn't able to answer. I'm going to try to get them all answered tomorrow, which still doesn't get you a lot of time for help, but try to get through all that. So I hope you got stuff that was useful. More than I was going to say 99.9 of the whole world population, but let's say engineers that have done robotic stuff, all they know how to do is like that example we saw with the Puma, where they took the forward analysis equation and threw a couple of terms over here and kind of hope for the best. And that can work for the simple geometries, but oh man, for the other ones, they're pretty complicated. So you know a lot more. I think about half of you are in Robots 2. Robots 2 is a blast. I love it. It's my favorite. So, yep. So I think that'll be, oh, if you are in Robots 2 though, I hadn't sent the note out yet, but let me show you the text that we are going to use. The text, because you're going to want to have access to it. What are they selling it for? Screw theory, robotics, come on. You should put us on top. So, what are they going for now? It's too much. 85. Oh, and that's for a hardcover. I think they also do like a Kindle-y thing. Oh, wow, the Kindle's even more. That's ridiculous. So, so it's a good one. The only thing that was funny about, we're 1 minute over, but I actually drew that picture in SolidWorks. The table is actually a table in our lab, so it was all measured out, and I put that all together and I sent it off to Cambridge, and they added the text, and they sent it back as if they had just like invented quantum theory or something. Like, look at this great job we did on the cover of your text. You know, and all they did is put the words, the letters. So I think I did the hard part. But again, if you're in that class, if you're not in the class and you're thinking about, you need something to take, it's a blast. I love Robots 2 stuff. We're going to do velocity acceleration stuff. The worst thing, like I would run from that class in a heartbeat if what we did was to take our position equations and try to take derivatives. How are you going to do position equations in general 7R? It doesn't do that at all. It's very visual, and again, based on the geometry. So I hope you had a good semester. I'm kind of dragging this out because I kind of hate to have the semester end. I feel, whatever. But you all been a really good class, and we'll see you, and good luck on your future stuff. Okay.